Hello, so today we're going to be looking at reaction 14. Now, the first thing that we want to do, let's take a look at our reaction here, is we kind of want to figure out what type of reaction it is because that will give us an indication of how the mechanism of the reaction will occur. So this reaction type is a crossed aldol condensation. And how do I know that? So I gather all my information from my reaction that's present. The two things that I notice outright is we have two enolizable carbonyl compounds present here that kind of look like they are adding on to each other or connecting in some way to form a bond to create this product. So that's kind of a first indication. And with our product, that actually gives us a lot of information too. Looking at this product, we can see that we have our carbonyl carbon, which is located here, connected to our oxygen. And then at the alpha position and the beta position, we have a double bond. So we can tell that this is an alpha beta unsaturated carbonyl compound. Unsaturated meaning not all the hydrogens that could be present in these positions are present, and therefore we're sharing electrons, building that double bond. Between this indication of the type of product we have and our reactant and our reagent, I can tell it's going to be an aldol reaction of some sort. We can also tell it is a crossed aldol condensation because we not only have an aldehyde present, but we have a ketone present as well. And then the last little indication here is the condensation. We know that with the heat, we are going to be losing some water, creating condensation, hence the name condensation. The last thing to kind of look at and kind of understand is this crossed aldol condensation could occur in a basic or acidic conditions. In this case, we're going to be in basic conditions, and we can note that by the potassium hydroxide. The potassium hydroxide is a really basic compound, so we know that it is our basic conditions. So the first thing that we need to do is we're going to look at our reactant. Now we're going to put all of our little electrons in there. We're also going to put them on here, on our oxygen down here. And then we also have some electrons on our potassium hydroxide. Now this oxygen here, so if we do this, kind of split this in half, kind of keeping in mind what charges are kind of present in this compound. We know that this oxygen wants to reach out with its available electrons to grab this hydrogen. So we've grabbed the hydrogen, and the electrons here are going to go from our bond from the hydrogen to the carbon to jumping onto just this alpha carbon here. So that's going to give us a negative charge in this position. Now it's interesting to note this occurrence could happen on this side of our structure just as easily as it could happen on this side, and then our benzaldehyde would just be connecting on this side. The reason that we're going from here is just kind of to show in theory the mechanism, but in reality it's important to remember that it could happen at either side because both of these are alpha carbons with hydrogens. It just is going to be really whenever this base comes in contact with whatever side first is going to be the one that's going to be activated. In our situation, we're going to say this side is the one it came in contact with first, and so we're having that activation in that particular alpha carbon. So our next step here is we're going to actually have the attack mode, and this is what we typically see with our nucleophile attacking the electrophile. We've activated this alpha carbon, and we have to determine which one is our nucleophile and our electrophile. So what's interesting with this reaction is you kind of usually see the nucleophiles sitting in this position, but in this case, the benzaldehyde is actually going to be our electrophile. Kind of two things. We activated this area to carry out the attacking mechanism, but the other thing to consider is with your aldehydes actually have a more electrophilic carbonyl, which is this guy right here. And the reason why it's more electrophilic compared to the carbon and the carbonyl in this location is kind of looking at the nature and the structure of what a ketone is. The ketone has R groups on either side attached, whereas we know with the aldehyde, it's going to have an R group on one side and it's going to have a hydrogen on the other. So with the ketone, there is more steric hindrance and bulkiness and crowdedness going around this carbon here. It's going to be harder to be reactive. So this is actually going to be the more electrophilic one because it's, let's say, more available to be attacked. So we're going to come in, we're going to attack this, and we're going to put our little electrons in there. And when we attack this, these are actually going to, everything's going to kind of shift, and these are going to, electrons are going to come up here and be on this oxygen. So we're just kind of moving that negative charge from here to here. Now we're going to have a bond between this carbon and this carbon. So with what that kind of looks like in terms of the intermediate, let's go ahead and put all of our electrons in just so we can keep a tab on them, see what they're doing. Now we have more electrons on this oxygen because we shifted it in our attack. So this is our intermediate. We now have that bond between those two carbons that we talked about. This used to be the carbonyl carbon. And now we have this negative charge on this oxygen. What our next step is, we want to take this intermediate and transition it to the beta hydroxycarbonyl compound. In order for us to do that, we're going to need to carry out an acidic workup. And I know it's kind of confusing because I put that here, but we're doing kind of our 1 and 2 steps right here with our intermediate to the beta hydroxycarbonyl compound. So we're going to come in, let's use this hydronium ion, and we're actually going to just like pull one of these hydrogens off, and then the electrons go to the oxygen from that bond, because our hydrogen is going to come over here and it's going to appear right there. So that is now our beta hydroxycarbonyl compound. Beta hydroxy, hydroxy meaning the OH there, and the beta, because this is our beta position. We have the carbonyl carbon, alpha, beta. Now, with this resulting beta hydroxycarbonyl compound, our next step is going to be that condensation step. Now, I put this hydrogen in here just so that we can see it and we can visualize it. Of course, we have with our skeletal structure, as always, we have assumed hydrogens among that, but I wanted us to see this hydrogen here because this is what we're going to take with our condensation and our heat. We're going to lose water. They actually call it the condensation reaction because when they heated it, you could actually see beads of water appearing on glass container of whatever is holding the reaction. And we're going to lose this hydrogen and this OH here, pulling these electrons up, grabbing this over here. These come down. We're moving our electrons here to build that double bond between that alpha and beta position, which is going to bring us back to what we kind of talked about with our alpha beta unsaturated carbonyl compound. In this case, we're going to have a resulting ketone because we have an R group here and an R group here, and there's our double bond. So that is reaction 14. Thank you for sticking with me on this. Coming back to a little bit of a review. So we had our activation step with our basic conditions. Activation. We had attack from here. So this is our reactant is our nucleophile. So this is our nucleophile, and it's attacking our electrophile. Then we kind of have this halfway step where we have our intermediate. So we have the intermediate, and the intermediate undergoes an acidic workup. And then this, because of the acidic workup, we're adding that hydrogen here, which is our beta hydroxy. So we formed this beta hydroxy carbonyl compound. Now, if this was an aldol addition, we would be done here, but we're not because it's a condensation. And so our last step is to remove the water, and then we have our resulting unsaturated carbonyl compound, or alpha beta unsaturated ketone. So activation, attack, acidic workup to build the hydroxy product, and the heat to get your product. Thank you.